Hi everyone, welcome to part 2 of this practical. So in the first part we looked at how to load in netcdf data. Now what's really nice in MATLAB is you can actually write to netcdf as well, and I've used that function quite a bit. And then we plotted the data, so let's just run that again. So we loaded in the data and then we produced 3 plots, the whole data set, just for 1 year, 1996, just for 1 month. We can start now. Bear in mind, this is total water level, so this has the tide, but it also has elements that aren't the tide, the weather as well. Okay, so what we're going to do now, and I'm just going to go back here and switch off this NC display because I don't really want this printing to the screen every single time. I'm just going to put some semicolons here as well to stop that printing to the screen. Okay, so step 3 now is we are going to do a tidal analysis using some software called UTide. And we're going to do that for 1996. Okay, now the nice thing about MATLAB is there's lots of additional packages. So let's go to Safari or Explorer, wherever you're doing. There's lots of additional packages that people have written and they're stored in this MATLAB Central. So if you Google UTide, this is some software that has been written by this particular person here who's at the University of Rhodes Island. There's a nice little manual as well. But he's written a set of MATLAB tools called UTide, and you can download them here. Okay, let's go back to our setting here, back to our folder, downloads, and there you can see the UTide version. So I'm going to drag that into our directory there. And you can see that there's 2 main codes. There's this reconstruct and this UT-solve. There's also a PDF report here that you can read as well that goes into a lot of the technical detail of how the analysis works. But hopefully you've all watched the videos and you can see how we do an analysis. Now what we need to do is, in order to run those tools in a different directory, we need to go back here and we need to, let me just expand this out, we need to set the path. So if you go to set path here, I'm going to add with subfolders, go to Practical3, I'm going to add this folder to the path. Okay, that folder is now in the path and that folder is UTide. So I can save that. So if I call any functions now, from UTide, it doesn't need to be in the same folder, but that's in the MATLAB path. So it will check all of the MATLAB paths and if there's a command in there. Okay, so first of all, let's just extract the data using the find function for 1996. So we're going to say TS2, we're going to use the MATLAB date time is greater than or equal to date time. And remember, it's the year first. So it's 1996. We're going to go from month 1, day 1, 0 hours, 0 minutes, 0 seconds, and TS2 that is less than date time, and we are going to go 1997, 1100. We can just run this little bit of code, and again, I gives us the row numbers. Oh, sorry, I put date num here instead of date time. So let's run that. Okay, so I gives us, sorry, I'm still doing something wrong. So we have date time, that, and TS is less than date time, that. Let me just run that again from the beginning. Okay, it's telling me there's some sort of error. Numeric input data must be a matrix with 6 columns. Trying to work out what date time. Oh, I think what's wrong is, you can see here, it should be 6 values, so I made a mistake. So normally the good thing with MATLAB is if you do make a mistake, it normally tells you what the error is. Okay, so now we have the row numbers, and 8784 is good. I know that's the number of hours in a given, that's a leap year. There's always that number of hours, and you can do that. You can say 366 times 24 and it should equal 874. If it's just non-leap year, there'll be 8,760 hours, so that's right. Okay, so just to make things easier, I'm going to do a TS 1996, and that is going to be TS just rows I. I'm going to do a TS2, because with a tidal analysis we can't use date time, unfortunately. It often only accepts the date number and then the water level. Okay, so if I run all of this again now, and in fact what I'll do is I'll just, so now you can see we've got this water level just for 1996, and I can get rid of I because I don't need that anymore. And now let's do our tidal analysis. Okay, so what I'm going to do is TA stands for tidal analysis, and this function is going to get the coefficients, and the function you use is utsolve. And if you copy utsolve and put help utsolve, because we set the path, it should find it and it will tell us how to use this particular function. Or you can actually open it as well. You can say open utsolve and it will open the function and tell you how it works. Okay. Now I'm going to use this for I used to use an older one called T-tide, but I've only used this one. So the first thing you do is set in the time. Then you set the water level, 1996. Then you have to have an empty matrix, just trying to remember why that is. So you have an empty matrix there. Oh, that's because we're just doing this for water levels. We're not doing it for currents. If we were to do it for currents, you'd have a U and V component, so that's why there. Now, whenever you do a tidal analysis, it needs to know the latitude. Now, I'm going to put in a couple of other things. I'm going to, you can look at the help menu to work out what all of these are, but these are things like, so the constituents, I'm just going to do auto. It's going to find its own constituents. I'm not going to fit a trend. You can get that to fit a trend. Now, this does the confidence intervals, and it's going to be based on white noise. All of these, you need a little bit of expertise to interpret this. I mean, you can use the default settings, but I'm going to use this just because I'm familiar with this code. But I can talk to you about what some of these settings mean later on if everyone's interested. You can actually cut it off after here if you want to not use any of that, but we're gonna leave that in. Okay, so let's just run everything again, and then we can have a look at what the results look like from this time. So you can see that in the past this would have taken days and days to do using that tide machine created by Lord Kelvin. But now you can see it's run it in a couple of seconds and it prints some stuff to the screen. But the important thing is this TA coefficient, and this is what's called a structured array. So within there's a name. So this is the name of constituents. So, and it does it in order. So M2 is the biggest constituent for this type, then S2. So those are the two main diurnal constituents. The fact that those are the biggest is probably going to indicate this is a semi-diurnal site. Then we have K1, then N2, O1. And you can see that it's fitted 67 constituents. Now, with a year, it's normally 67. If you have more than a year, it can fit hundreds. But if you've got less than a year, it typically only fits 67. So that's the name. And if you go into A, this is the amplitude. So M2 is 1.86, S2 is 0.53. You've also got the confidence intervals. So it tells us how confident we are about those. And then G is the phase. So 118 degrees is M2, 168 degrees is S2. Okay, so there's your tidal analysis. So you can see actually it's incredibly simple. It's just one line of code. So now before we do a tidal prediction, let's plot the size of let's plot the size of the constituents. I always spell constituents wrong. Okay, now again, I'm going to actually borrow this switch figure code because later on I might not want to produce all of these plots if I run this through for multiple sites. Okay, and once again, I'm going to borrow the same code here. In fact, let's just cut and paste this because I'll borrow this and edit it. So I'm going to have 3 subplots. Okay, on this first subplot, I'm not actually going to use a plot now, I'm going to use a bar. How do you think you do a bar chart? Well, it's the word bar. Again, you can type help and work out what that is. So we're going to do a bar chart, bar, and now, in fact, before we do that, I'm just going to put this to a new matrix. So I'm going to say con for constituents, and the name is, I'm going to convert it to a string, is going to be TA coefficient, and with a structured array you use the dot name, and then con A is going to be capital A here, so I can run those two lines of code and just check those works. So now I've got this con A and con N. Okay, so I've just kind of extracted the data from this coefficient to make it easier to work with. So now I'm going to do a bar chart of con A. Okay, and then this time I'm going to have an X label. So the X label is going to be the title constituent. Okay, and the Y label will be the level in meters. I'm going to set the font weight. I'm going to do that. I'm not going to bother with the title. You can always add that later. Okay, now let's run this. Okay, now these are each of the constituents, the 67 constituents. As you see, lower down, they're incredibly small. So really, you can see it's it's these ones. It's 1 to 39 are the biggest, and in fact, you can see that the top 10 are all quite large, and after that, it gets very, very small. Now, this number isn't particularly helpful. So what I'm going to do is actually change the label. So we're going to say set A1, and we're going to do xlim. And the limit is going to go from 0 to the length of con n, and I'm going to add a 1 at the end. And then I'm going to set the x tick, and I'm going to plot the tick from going from 1 at intervals of 1 to the length of the constituent. So there'll be a tick for, if we run this, you can see there's all 67 constituents. And then what I'm going to do at the end is I'm actually going to use 3 dots just to get onto another line of code. I'm going to set the X tick label. I think I spelled that wrong. X tick label. And this I'm now going to set as con n. So I'm actually going to set the names. So you can see M2, S2. Now this looks a bit of a mess because there's too much going on here. So what I'm going to do is there's another nice thing called X tick label rotation, and I'm going to set that as 90 degrees, and what you can see is that will pop the label on the side. So there we go. So now we've got M2 is almost 1.8 meters. S2 is 0.53, K1. So you can see actually the majority of the constituents are in the top 10, and then they get smaller and smaller and smaller. So I know what most of these constituents are. I can never remember off the top of my head what some of these other ones are, but you can always go into the literature and find out what those are. I'm just going to take out the meter here. Okay, now what I'm going to do is I'm going to actually plot the percentage rather than the actual size. I want to know what percentage is of M2. So I'm going to say con, and I'm going to make this row 2. So I just need to go here and make sure I only plot row 1. So con 2, sorry, it's not con, it's con A2 is going to be, first of all, I'm going to have circular brackets. Is going to be con A, all the rows, column 1, divided by the sum of con A, all the rows, column 1. And then I'm just going to times everything by 100. So basically, I'm just dividing this by the sum of all the values and timesing by 100, and that's going to give me a percentage. We can run this, and that should give me a percentage. So let's go back to con A. So you can see that 1.8 is actually 35%. So 35% of the tide is made up from M2, 10% is made up from S2, 6.5% is made up from whatever the third one was, K1. So now I can copy this line of code again. It might sound silly having this switch, but you'll see later on it becomes quite useful when I don't want it to plot this for when I loop through multiple sites. Okay, so now I'm going to change this to A2. I'm going to plot that to A2. Just go back down and make sure all of these are A2. And now I'm going to plot column 2. And rather than a level now, it is going to be a percentage. Okay, so let's run just that section. Okay, so you can see it looks exactly the same, but now it's a percentage, so it's 35%. But what was more useful, actually, is rather than a frequency kind of plot, it would be useful to have a cumulative percentage, so you can kind of see it adding up. So let's call it cumulative percentage. And now to make it cumulative is quite easy. So we're going to have a third column. There's actually a function to do this, and it's called cumSum, cumulative sum. And we're going to do that on con A, all the rows, column 2. So let's run that. We can go back to con A and have a look. Con A, comma 3. Oh yeah, sorry, there it is. So the first one's 35, but now it's going to add them together. So it's going to add 35 to 10, 45. So what you can see is as you zoom along here, if we go down to say 80%, so 80% of the tide comes from the first 14 constituents. 90% of the tide comes from the first 24 constituents. So you can see that actually even using fewer constituents gets you the majority of the way there. And it'll be a bit clearer when we plot this. So let's plot this as number 3. Number 3, make sure we go to 3, 3, and make sure now we plot this as number 3. So we can run that again, and here you can see a nice cumulative. And I'm going to make that slightly better by just adding some lines. So I'm going to plot and 0 to the number of constituents. In fact, I'll go from 1 to the number of constituents, and this time I'm going to plot 80% because I'm just interested in when 80% is reached. I'm going to do a dotted red line. I'm going to do the line width is 2. I'm going to cut and paste that code, but instead of 80 I'm going to do 90. And there you can see, so you can see that 80% is reached by these constituents, and then 90. So you can see that 90% of the constituents, 90% of the tide is made up of the first sort of 24 constituents. 18 is made up of the first, I think, of 17 or 18 constituents. So there we go. And now that we have our constituents, the next stage we can do is actually calculate the form factor and the tidal range. So remember, the form factor is whether it's semi-diurnal, diurnal, or mixed tides. And remember from the notes, this is based on an equation. Okay, now what I'm going to do is, because this constituent varies in order. You'll see this when we run another site. It might not always be that M2 is the biggest. For a diurnal site, it might be that K1 and O1 are bigger. So what I'm going to do is just find, so I'm going to say C1 is find, so constituent 1 is find, and I'm going to use this string CMP function. And I'm going to find when comp n, when you have a comma, is equal to K1. So remember, the form factor is K1 plus O1 divided by M2 plus S2. So I'll just switch that off and just run this and check. Have I got the right STN-CMP, find STM con N, just seeing that I'm checking that I'm doing this right. So let's just run that from the beginning and check that works. Oh, sorry, it's going to do the tidal prediction again, so it might take a bit of time. Okay, so it hasn't found anything, but that might be because I need to put in capital K. Let's try that. Yeah, so that said row 3 is where K1 is. Yeah, that's great. Okay, so now I will do the same for O. So those are the two diurnal constituents, so those go on top. And then on the bottom is M2 and S2. So these are, so in most parts of the world, these are the dominant constituents. So it's row 3, we can check this, row 5, row 1 and row 2, very good. But that will vary depending on site, because remember the order is based on the size. So now what I'm going to do is I'm going to copy the constituent amplitudes into a variable called O for output, because I'm actually going to compare this across sites later. So in row 1, column 1, I'm going to put the constituent, in fact it's con A, and it's going to be C1. And again, I'd always encourage you to, it's very easy to make a mistake in MATLAB, so always check. So column 2, column 3, column 4. So I'm going to put in the constituents just so we can kind of check. Okay, so now we have this variable called O, and it's 0.3, so we can go back to K1 is number 3, so that should be row 3, which is 0.3. The third one, it should be 1.8, which is M2, yeah. So there we have K1, O1, M2, S2, and that's everything we need to calculate the form and the range. So let's first of all calculate the form factor. And I'm going to put this into O, column 5. So the form factor is really easy. It is O1, which is the K1 amplitude, plus O2, and then we're going to divide. You always have a dot there, so it's not matrix, and we can copy this again. We're going to divide it by 3 and 4. Again, we can run this. So the form factor is 0.26. Now, normally, if it's less than about 0.25, it's semi-diurnal. If it's greater than 3, it's diurnal. So we know that that is a semi-diurnal tide. And again, if we remember, I mean, we could tell this just from the plot. When you zoomed in here, you could see that there was 2 tides every day. So we know for sure. But later on, I'll show you, we'll do this. We'll change this. We'll download a new site that I know is diurnal. We'll run it again, and you'll see that this number will be much bigger. Now we can calculate the tidal range. And to do this, I'm going to use a loop. I'm going to say if O is less than 1.5, it's going to be semi-diurnal. So if it's less than 1.5, it's semi-diurnal. So if O is less than 1.5, then O, row 1, column 6, this is the tidal range now, is going to be just based on, if it's semi-diurnal, it's just based on M2 plus S2. So it's M2 amplitude plus S2 amplitude, and we times the whole thing by 2. Whereas if we have a mixed tide, so if it's greater than 1.5, it's mixed or diurnal, then it's going to be M2, because M2 is still large in most places around the world. And so you always have M2, but now we're going to bring in K1 and O1. And you'll see this later on when I run it for a diurnal site. So now we can run that, and the tidal range is 4.711 meters. That's just an approximation, but we can go in here and we can see that the tidal range, sure enough, is around 4.5 meters. So remember, this is just a simplification because it's just based on the M2 and S2. And later on, we'll run this for multiple sites and compare. Okay, so we're getting on really well in part 2. So let's just do a little bit more. So now we're going to get onto the fun bit. Is now we've looked at the constituents, we've used the constituents to predict estimate the tidal range and form. Now we're actually going to do a tidal prediction and isolate just the tidal component. So remember in UTide, if we go back to, there was 2 functions here. There's usolve, which does the analysis, and then there's this ureconstruct, which does the prediction. Okay, so what I'm going to do is say my output is going to be TI for tide 1996. So that's what I want to get out. And we can use this UT reconstruct. And this one's much easier to use because all we do is we put in the time and then we put in the constituents. So at the moment, I'm putting in the time as just 1996 but later on, I'll show you how to predict for 2020 or 2050 if you want. And then now that we've got the tide, we can actually calculate the surge. Let's call it SU for surge. Again, it's 1996. Is going to be the water level for 1996 minus the tide for 1996. Okay, and let's run that. And you can see that this will normally be quite quickly. And now we should have a tide. It should be the same length. So this is the tidal component. And we should have now calculated the surge. So now we've got the total water level and then the tide and the surge. So let's step 7. Let's plot that data and have a look at see what it looks like. Now again, I'm going to use this switch because later on I'm not going to want to do this for everyone. So notice how I always copy and paste code just because it's easier. Now this one, I'm just going to have 2 subplots. Okay, and the x-axis I'm just going to do on the bottom one, so I won't do that here. Okay, so now I can plot TS2, 1996, and the water level, 1996. I'm going to plot this as blue, and I'm going to do the line width as 2. And then I'm going to plot, this time I'm going to plot the tide as red. And I always try and use the same colours. Blue for water level, red for tide. Okay, and we will take that off for the time being. Let's just run that and have a look what it looks like. So yeah, you can see the total water level, now the tide. So you can see that very clearly here we had a big storm surge, and that should hopefully show up later. So let's bring up the storm surge plot. I'd like to add a title, but let's do that in a minute. So this will be 2, 2, so 2. So now I'm just going to plot one line, surge, and I'm going to plot this as, I don't know, let's plot it as black. I'm going to add a X label as well, because it's bottom plot, and the X label, what should we call it? Just date or something, or year. No, let's call it date because it'll be months. Okay, so here you can see we have a really big storm surge there, but we do have some other storm surges and some obviously some sort of low pressure there. Okay, so there you've done your first tidal prediction. Now let's add a title, and I'm going to be clever here in that I'm going to, oh yeah, I did this earlier, but I am going to, well, in fact, let's just borrow this title because I'm going to run this multiple times for different sites, so I'm just going to have the site name. Now really here as well, we should probably add in a legend because we have the total water level and then we have the astronomical tide. Okay, there we go. So that's the site. So well done. Okay, so let's just do one more. No, I think let's pause there and then I will do a third part in a minute.